All right, welcome back, everyone. Last talk of the first week of the summer school. 10 a.m. on Monday we started, and then we're now here taking it home. So I'm very excited that that Chris Collison is going to take us home to summarize a beautiful review paper that actually came out maybe just last week. Thanks to Chris for doing this on short notice. I messaged Andrew White, and then I asked him if Chris would do it. And so thanks a lot to Chris for agreeing to do this. And also they have created a wonderful GitHub repo that I think maintains all the various language models and agents that have been built for chemistry, material science. And so I think Chris will share about that as well. So without further ado, I'll hand it over to Chris. Very excited to hear about the work that you've done.
Thanks very much, Venkat. I hope everyone can hear me. I'm also going to say at this point, so my name's on here because of the presentation, but a big shout out to Mike Caldas Ramos, who between the two of us we wrote a lot, and this was I'll try not to keep you for too long before your weekend break, but this was actually a really, let's see if I can get things moving in here. This was a real labor of love, as I put it. I think we started working on this in January. It's about 500 citations in here, and about 100 or so different models that we looked at. So my background really is I'm a material scientist, a chemist. I used to work with solar cells and organic photovoltaic devices. And I went to Andrew a couple of years ago and asked him if I could join up and do a sabbatical in his group. And sort of the rest is history. I've been working with them ever since. And so this paper, I think here's the outline. But what I think the take-home message I hope I leave you with is that when we know about the application that we're working with, when we can ask deeper questions about what we're trying to do with the application, and then we can couple that to the AI itself, then we'll have a lot more productivity and a lot more more impact in the outcomes. So I'm going to pretty much follow along with the structure of the review article. So I'll talk. I understand this is you've been doing a lot with foundational models in the last week, so I won't spend too much time on the transformer architectures, etc. But I'll introduce them to you, and I'm going to probably spend more time linking that AI to the chemistry itself. So I'll talk about really what a chemist does, and then try to link each of these transformer architectures to suitable chemistry areas. So we'll be talking about property prediction and target-oriented inverse design and synthesis prediction, and then a little bit about automation. And then the automation actually leads to, well, how do we improve automation? So we work with the LLMs as the brain behind the autonomous agents. And so this will end up being a lot of survey of a lot of papers that are out there. But I want to spend a little bit of time at the end in saying how we can think about the challenges and opportunities, and these might be also pertinent to other people in different fields. And just one caveat in here. So we can think about with natural language processing, these are going to be often we're working with molecules. So how do we think about those molecules in terms of a text-based structure? So the first slide here really is, okay, so some context. So we've been doing AI and machine learning in chemistry for quite a long time. So very early computational methods. I'm not sure I'd want to call those AI, but the seeds were planted, and so we've move through this high throughput screening, which is about how we get a lot of data. And then we've moved into the RNNs and CNNs and GNNs that were popular in the 2010s, and so now we're into this latest phase. And so I'll start really simply. If we think about just an RNN, and obviously some of the problems that face us with RNNs is that if we're doing a translation task and the boy sits on his bicycle, so what we find is that we have to put all these words sequentially, one by one, in series into these hidden states. And so by the time, for example, we're thinking about, El niño se siente in su bicicleta, if we think about the word to sit in here for the boy, we have to go through all these hidden states. And so there's a big gap from sits to se sienta. And so in our sort of series-based RNN approach, we've got this big gap. We've got to include all the words and their orders in these hidden states. And so when we think about longer sentences, if we're interested in predicting what this translation would be of sits, the longer the sentences are, the gradients tend to vanish. The more words in the sentence, then we're going to have a gradient that is a small number raised to a higher power, depending on the number of words, or a large number raised to a higher power that either explodes if it's a large number, or it vanishes if it's a small number. And so you will know this, but what happens is, and so here's the story. We move into the Vaswani et al. Transformer eventually, which is what this review article is largely, that's the framework for it. But we think about attention, and so attention allows the position of a word to be coded, so we can parallelize. And so we can use, for our positional encoding, we can use these sine waves or cosine waves with different frequencies, which allows us to add a number sort of between -1 and 1 to the embedding of the word. The other, really moving through this quickly, so that attention itself is associated with we have a key, and a vector as a key, and if that aligns with the query, then we can get a larger number. And so ultimately our output, jumping forward really quickly, would give us we can get a highest softmax, or a highest probability based on that combination of the transpose of the key and the dot product, which measures this angle of alignment for the query and the key and the value. And so as you all know, this is where this attention works really well when we have very long sequences. And in our paper, we also used that basic the Vaswani et al. Picture, and this was developed for natural language. So tokens are words or subwords in natural language. In a sentence, we might have sort of maybe up to 15 to 20 words, and a vocabulary space. So there's a large vocabulary in here for natural language. And so the tasks we might do: text completion, question answering, and sentiment analysis. So we'll think about how that translates to chemicals with the same sort of transformer model. And on the right-hand side now, I'm also going to show something that comes up from one of the papers. It's actually a review article by Das et al., which I liked a lot. And in that paper, Das et al., they talk about this molecule here. So now we'll switch to a little bit of chemistry. This is acetaminophen, or as it's called in Europe, paracetamol. And so what we can do with SMILES, as you probably know, we can write this down in a text format. And so now the tokens become, well, one capital C, little c. We've got a double bond in here, so it's an equal sign. And the sequence length can be quite long. The vocabulary space is usually a lot greater, or sorry, a lot less than the text-based vocabulary space. There's only certain atoms that we might want to include. or only certain tokens that we might want to include. There's other problems that exist though. So a valid smiles, we may actually have a valid smiles, for example, that has carbon attached to 5 different atoms. So that smiles, according to the syntax or the grammar rules of smiles, might be correct, but it might make less chemical sense. So later we'll think about how we measure for validity of a particular smiles molecule. We also have multiple smiles, these text strings for the same molecule. And so these are the chemical representations that go into the transformers. And the tasks that we're going to be thinking about, property prediction, molecule generation, and synthesis prediction. So I'll talk a little bit more about those as we move through. The architecture. So again, I'm going to present the tasks. The tasks in chemistry line up really with the transformer architecture. So the encoder only approach is what we use typically to extract some sort of chemical essence from the smile string. Is can we learn something about the chemical properties from the smile string that text that we put into the transformer? So we use an encoder only to measure essentially a vector or some numerical property that comes out of the smile string. And then we also, we've represented this in one picture in the review article, kind of separating them out where we need to. The decoder only approach is that's obviously an autoregressive, so we get new values depending on previous values. It's a causal response. So we'll use this for predicting new molecules. And then the encoder decoder, that was obviously how the transformers were developed for translation tasks. It turns out that chemical synthesis predictions can be aligned with the translation tasks, like in natural language. So now, kind of, that was my summary of the transformer. I'm putting up a slide here that starts with a quote actually from, this was not intended to be a plug, but in a conversation I was at a conference recently, there was a representative from Microsoft Azure Quantum Elements, and he referred to how it's not supposed to be a plug, but Microsoft considers that chemistry is really, really important. And their quote was that chemistry directly touches more than 96% of all manufactured goods. So I thought I'd start with that. If we think about properties and chemicals and what they do, maybe I want to have an indicator or an actuator that tells me the pressure that's put on it in a pressure sensitive detection, gas pressure. So something where a crystal structure, when compressed, it changes color. So it has to have a certain property in order to do that. The molecule, we might have a light harvester for a solar cell, and that molecule has to absorb a certain type of radiation from the sun in order for the solar cell to work. We also have certain properties that enable a molecule to become a good catalyst that might speed up the breakdown of plastics in the ocean, for example. So these are various properties, and if I take a molecule, I want to be able to predict its property. We also we want to make new compounds that have certain desired properties. And wouldn't it be great if we could take a particular application and work backwards from that application and know what property we needed, and to instantly predict a molecule that would be a solution for that application. Once we've done that, we also want to synthesize, or can we synthesize the molecule that we've come up with using readily available materials, cheap, non-toxic materials maybe. And then the other sort of umbrella in our paper really is automation. So I'll show you later how chemical space is just huge. And so in principle, can we explore that entire chemical space to find a molecule that works for us for a particular application? One thing that will show up a few times here, by implication mostly, is that high quality data is going to be really important for accurate models.
Just a quick question. If you go back a slide, I think, or two slides, you mentioned that the vocabulary of chemistry is around, I think you put it at like in the order of 100. And I guess I was just kind of wondering where, like how you think about that, because I think most of like the converters, the molformers are significantly larger than that in terms of the token count by at least one or if not two orders of magnitude.
And so let's, what I'd like to do is basically say, this is my comparison with character space for words or natural language. So in other words, it's probably 2 or 3 orders of magnitude less than that. But I suppose if we just think about smile strings, what are the different ways in which we can, I mean, we can have the regular expression, we can have reaction smile strings, so that this sort of a more kind of hand wavy way of sort of comparing it to the vocab space for text for natural lange. So
gotcha.
Don't take me too
just
don't hold me to that one.
Thank you.
You're welcome. So and again, forgive me, I'm a little bit of originally a chemist, so we think about imagine a molecule, and then I think what would that property be, right? If I take a molecule and often we find maybe someone's gone out and found a sea squirt in the ocean, and they've pulled a chemical compound from that animal. Evolution has allowed that animal to make some chemicals that end up being defense mechanisms against diseases. So this is often where we start as chemists, with these natural products, but maybe it doesn't work for humans, or we want it to cross a membrane or a blood-brain barrier, or we want it to decompose in such a way that it's non-toxic. So these are things that chemists think about. And so on the top right here, I've also got this idea, well, we've also got, for proteins, for example, we've got amino acids, and then we've got combinations of these amino acids actually lead to these sort of secondary and tertiary structures in a protein. And it's the shape of that, the 3-dimensional shape of that protein, that has a huge level of importance for drug design. So these things are important too. And then, for material scientists, this is polymethyl methacrylate down in here. So this is a methyl methacrylate molecule. If I couple these across this double bond and I keep adding these units together, then I end up getting a really long polymer chain, and the polymer properties are a function of the length of that chain, and also that we might end up having these branched or cross-linked chains that even strengthen the material more and more. And so what we find today is we rely a lot on polymers and plastics, and we rely on our knowledge of proteins for therapeutics and drug design. So a chemist kind of thinks about all these things. And I'll skip this one, but here's the process again. We might have this natural product, and we might want to modify it a little bit. The chemist imagines tacking on a hydroxy group or something. We synthesize a molecule, and we measure the properties of that molecule. We test it in the application. Oh, it doesn't work. We go around the loop again. And so this is kind of what we do as chemists. So sort of now what I'm going to do is just go back now with that introduction to chemistry to some of these now more nuanced chemistry tasks. So we'll start with property prediction, and sort of getting back on track here. And so if we think about the encoder only architecture, so all of the models that I'm going to refer to today are these bidirectional encoder representations from transformers, these BERT type encoder only models. And what these were used for originally is to get some sort of semantics, get some measure of, if I say chemistry is great, well, we might say, well, oh, I like that. That's a positive statement. So we might put a number and get some sort of happiness value from the statement beyond just the words that are used. And the same thing is if we plug in these, this is just an example, right? We just plug in these amino acids, just an illustration or a cartoon idea. So maybe we can extract some chemical essence from these smile strings down here, and we end up perhaps, if it's trained appropriately, then we can, recognize that we come up with a prediction of valaine's acid dissociation constant in here, pKa. So these are things as chemists we're interested in. So we're trying to get a deeper understanding of that input. And so that's why this aligns with property prediction. And often we're going to see it's always unsupervised training. So large data sets work really well for us. And so another thing to think about is, we may be interested in, this is an example of a smile string for a molecule I kind of made up. But we've got an oxygen group, a carbonyl group here, and a hydroxyl group here. It could be that some hydrogen bonding between these groups in here actually dictate the properties of that molecule. So how do we kind of extract that deeper meaning from this smile string, given that these oxygens are actually so far away? And I think that's the beauty of the transformer work, and in being able to extract even three-dimensional information from a string, right? So kind of want to hero of mine, I think, was Philippe Schwaller, and what he and his group have done in recent years. They've spent a lot of time thinking about synthesis. And before I go on to property prediction, encoder-only models were also originally used, and I think this was one of the first instances of use of these transformer models for classification. And what Philippe did was classified some complex synthesis reactions from these raw smile strings, and he found that the atom rearrangements could be extracted, so that we're able to classify some of the results from here. And that ultimately, hand wavy here, but basically allowed some acceleration in chemical synthesis prediction. So we'll return to that a little bit in a few minutes' time. And I wanted to add that in because there are some other methods or other tasks for encoder only, but most of the time it's in property prediction. And one of the first models that I could find on this topic was the Smilesbert model. And so these were pre-trained on these really large unlabeled zinc data sets, and then were fine-tuned on labeled data sets. And in this particular case, they fine-tuned with a water octanol partition coefficient, essentially how well certain molecules, whether they stay in water or whether they stay in octanol, and that's a regression task. And so they could effectively get fairly good accuracy on these log P data sets that were tested. It was a test train split in here with these pairs of smiles with the appropriate properties. So this is one of the first models. There's also so again, all these titles are going to be property prediction on the top here. This is the molecule attention transformer. So we're starting to see some evolution. This was from February 2020 from Mazziaka. And what they were able to do, so they actually input some interatomic distances into the transformer model. But they paid attention to that. And then they also, with that in mind, they got a competitive performance on certain property prediction tasks. Most of these the data sets that they are applied to, the downstream tasks, were often taken from the molecule net data set. So we'll talk about that a little bit later on. 60 actual practical molecular data sets were used in this multitask learning BERT, MTL BERT approach. So again, this was the breakthrough here, was that this again was large scale unsupervised pre-training on a large Kemble database, and they fine-tuned on many relevant downstream tasks and on this molecule net benchmark data set. And so they were able to get, again, better performance. So a lot of these slides here are basically just showing evolution wise how some of these models started to gradually improve. And I won't go through any of the nuances really in how they did it, but some of those, we can't put that all into the review either, but the papers are all there. So again, evolving a little bit further, and some of the differences now with MolBERT. So again, also trained on these large unlabeled data sets, but they actually used another type of molecular representation, a Morgan fingerprint, which is a 512 bit vector representation. They actually generated that from the SMILES and plugged that into the transformer, and they were able, again, with their sort of small tweak to the process, were able to demonstrate better accuracy. And then we've got MolFormer. So they've used a different type of positional encoding. So there's all these groups are trying something different to try to extend the accuracy. And this is really interesting because they, again, they learned these spatial relationships between the atoms. Like I showed earlier, maybe there's some level of three-dimensional chemical essence that's being pulled out of the molecules. And so they also said that they were able to predict some quantum chemical properties that was faster and more accurate than density functional theory. So DFT is very time consuming. So the idea here is that, can we get, with lots of data, right, can we get more accurate and faster predictions of properties than we can with sort of quantum chemical calculations? And they claimed that we can. They've also, for the first time, started to talk about, in their paper, environment, the impact on the environment of using GPUs in general. So actually, that was interesting to me that they mentioned that. Again, there's a GitHub package that you can, or repo that you can work with there. The two Chemberta papers out there, again, this is just for addressing the slide on the right hand side. Again, what they're trying to do is demonstrate improvements. But what I liked about these papers is that they talked about now how, if we can scale to more data for pre-training, do we get better accuracy? And the answer is yes. So they tried different data set size inputs. They also tried a different tokenization strategy. So they used this regular expression from Philippe Schwaller's work. That ended up being better than the byte pair encoding approach that was more traditional. And And then they also used smiles and selfies. So selfies by default that was developed so that every way that you represent the molecule with a text string, it gives you a valid molecule. And that's not always the case with a smile string, but it turned out that there was no difference there. And then Day 2, they've basically added some multitask regression. They also start to look at even larger pre-training data sets. This was another approach. Another group here demonstrated some improvements with using selfie strings, but by and large, this is, you know, the movement is to gradually improve the property prediction approach, or accuracy rather. And the last one I wanted to highlight was one that I quite like. I'm very impressed with this paper. Like I've mentioned earlier, if I have a essentially a smile string that's a bunch of letters, and here's what I see as a two-dimensional picture. This is how I might draw this molecule, but of course it's a three-dimensional molecule. And what they did is they've applied from smile strings. They've tried a transformer approach. They've applied this to the free-solve solvation-free energy data set. And that depends a lot on the conformations of these molecules and certainly the three-dimensional structure. And they've actually managed to do a good job just from pulling information out of these smile strings. So I'm not sure how they've done that, but it's I guess a lot of the time it's empirical, right? And it's been demonstrated to work well. So that was encoder only. Decoder only. So now we're thinking about how to make molecules. So causally, right? If I say chemistry is great, the inference might be, well, let's go and use it to save the world. If I input two amino acids, then maybe you could infer that we need a dipeptide, and here's or two amino acids bolted together. We put some constraints around this, then maybe we can develop certain molecules based on what's going in and what's training these models. And a lot of this all comes back from the Radford et al. Paper, the generative pre-trained transformer. I kind of skip over this, but basically these decoder only, molecular LLMs where we're putting in chemical language. What are we trying to do? We have these desired chemical properties. We have certain constraints. We can train decoder only on these properties and constraints. We might be able to change the temperature a little bit and get more risky and creative selections. But the idea here is that we could, it's better to be able to come up with new molecules, especially if we can predict their properties in silico, rather than going out and killing a whole bunch of sea squirts and pulling new natural products from them to do our chemistry. So this is called inverse design. And in principle, wouldn't it be great if you could just take a property and in one step generate a molecule that gives you what you want for a target property? So early success was seen in this first paper by Adilov in 2021. And this is a t-SNE graph in here that basically what they've done is they have a certain molecule that has a certain property, and you can in principle generate different molecules that kind of have the same type of property. And so these generated molecules that are all slightly different, have a slightly different structure, have more or less the same property, but they're in a different part of the chemical space. So this type of drawing in here shows you chemical space. So the larger the, I've got these two blobs in here. These are very different molecules to each other, but they might have sort of somewhat similar properties to an original, maybe a drug for a particular protein target or something like that. Very hand-wavy explanation. What this is a busy slide, but there's another really nice paper by Bagel et al. in 2021. And the reason I like this paper is because they start to, in really great detail, talk about long-range dependencies within a molecular structure. They do consider the validity of molecules, so you can have various SMILE strings that aren't valid. A lot of molecules in the Chembl database are not valid molecules or have never been synthesized. So there are all these things that we start to think about, various structural rules of valency and ring closures. And it was in this paper, they outperform variational autoencoders, and so some of the metrics here I think are really interesting. So the validity, it's the percentage that are of the molecules generated that are chemically valid. The uniqueness, so you don't want to have 500 molecules in the same set of generated molecules that are all the same. Then there's this FCD term, which is about the similarity between the molecules that you've generated in the decoder only approach compared to the reference data set. And then also you've generated all these molecules, and so what's the distribution of molecules in the new set compared to the original set. So these are kind of were introduced in this and set the stage for how we might think about decoder only success in chemistry. And a couple of others that caught my eye was this Tiger model by Mazuz et al. And what they've got in here, this graph basically says that their model, the size of this blob in here, basically tells you the diversity value of all those new molecules that you've generated. You want to maybe have a large diversity of new molecules that all have the same, in here, the quantitative estimation of drug likeness. So a set of molecules that are all very drug-like, that are all highly valid. And so this was their claim. So as we think about generating molecules that are drugs, these are things that tell us how good the model is in getting us those new molecules. And there's another paper I liked, CMOL GPT. This was working on protein binder pairs, actually fine-tuned with also from data from Molecule Net. So we tend to work with data that's in one benchmark that may restrict future generalizability. So that could be a problem, but it was a nice approach. So again, this is this kind of TISNI, this reduced dimensionality description of the whole space of the molecules that were generated. And there are sort of certain dark, these are all little families of molecules, and certain dark blue in this case represent new molecules. And so this demonstrates branching from add additional functional groups onto a certain family of molecules that meet the same property, presumably the same property expectations. But something that also comes out of this is there's other idea that in principle we've got 10 to the 180 different possible molecules in the universe, or that could be made. So how do we even get there if we're always sort of still sticking around the original family of the molecules? So diversity is really important. You'll probably be pleased, and I'm not going to go through all of this, but these are some of the models that we went through, and I'm not even going to put pictures up from these, but there's a whole bunch more decoder only models out there. Each one is kind of showing a little bit more improvement over the last. And summing up this section, again, there's a great paper by Goel et al. Where they're talking about, again, the whole chemical space, so 10 to the 60 or 10 to the 180 is really big, right? And so how do we explore different molecules within that space, and what are the challenges there? Can we do that or are we really sticking to the constraints of the model? So there's lots of room for improvement there. Lastly, just a few slides here on the encoder decoder architecture, and the idea here is that I've got these same amino acids that are going in, and this is just a translation. So all these atoms still exist on the right hand side. It's just when I bind these two together, I end up getting a water. So there's all the same number of atoms on the right hand side and on the left hand side, so I can map where those atoms go to at the beginning and end of those syntheses. Time is getting away from me, so this I'll probably fly through this. So this is synthesis prediction. Again, Philippe Schwaller kind of starts to ask all the questions that we need to ask for a synthetic chemist, and started to think about how you could do this with machine learning.
Chris, maybe yeah, Philip actually covered it, so he presented on the first day, so I think we can jump through a few of these.
Okay, excellent. Yeah, so yeah, basically natural synthesis is really what occurred to me as well is we've got this level of sophistication of chemistry, and then we've got a really high level of sophistication of machine learning. And it may not be that you have really high level of machine learning sophistication. You still might not be able to apply it to some of the really big problems in chemistry. You know, this is I think an anti-cancer or immunosuppressive agent in here, discodermalide, 36 steps, many years that was made to make this particular molecule. And so, you know, synthesis prediction really challenging, and I'll fly through it. Yeah. So as you change one synthesis, you change a whole bunch of other things, knock-on effects. So that's what makes it really difficult. And if Philippe talked about retrosynthesis, you know, you have most chemists start with the molecule they're trying to make, and they work backwards to molecules you can buy. But really, when we think about the actual doing it in the lab, we go through in a forward direction. So I won't go through this, but it just gets really complicated. And again, the thought here is that if we understand chemistry and we understand machine learning, we can bring sophistication in chemistry and sophistication in machine learning together. And so the kind of the slides I've got is really, in this case, just a summary of what's in the paper. But the point here is that you get really low accuracies for, and this is long short-term memory RNN type work initially, but this is how it was started. But we gradually moved from 37.4% accuracy to some kind of template-based, you know, with rules-based approaches that are less free-form. But still, there's another busy slide. Sorry about that. But some of the points here is that you know, Philippe, most of this work is actually Toniato et al. It's in Philippe's group. We're trying to improve that accuracy, and we're still not getting up to 100% very quickly, because it's a really complicated task for machine learning. Nonetheless, you know, maybe agents can help. I'm going to jump in. So that was a really quick run through on synthesis tasks. Multimodal LLMs, there's a section in the review about this. Any person looking at this picture can say, well, it's a cat sitting on a computer. You don't need to be a domain expert to label this. Labeling for chemistry, for properties, if I want to come up with a labeled data set, it's really difficult to do that. I need domain experts. And so certain groups have tried to take you know, a molecular input and maybe a SMILES representation and train a multimodal LLM with some kind of caption that gives some level of property description for that molecule. And the idea here is even can we learn from literature? Can we read literature and pull out potential molecules that do jobs for us? And so that's the idea here. So I'll kind of fly through this as well. But that's the idea of multimodal work. Everything so far has been SMILES strings, but now we take data, we take NMR spectra or mass spectroscopy spectra or images of crystal structures or all these different things. Ideally, we'd want to put them all together, and so that's going to improve our accuracy at the end of the day. So we're of time, and sorry for belaboring the chemistry part here, but in the review, there's much more multimodal work. This is really good for pulling from papers. We can classify compounds or reactions or properties by just looking at the text. In principle, there's a bunch of different approaches using textual scientific LLMs for data capture. Huge list. So this is where I'm getting kind of to the end, and in the review you'll see these tables that Mike put together, and this is where you can find all the dates and the names and what these models were trained on. So decoder only, and then encoder and there's another summary table. So it's just a plug for the paper and Mike's work. Now kind of moving towards the agents, it makes sense to just talk a little bit about ChatGPT and chemistry, and this was sort of a kind of moving through ChatGPT. ChatGPT 4 Omni seems to be an agent at the moment, so this kind of improves every day almost, it seems. This Deb et al. Paper is really interesting, and what they did is they basically worked directly with ChatGPT to try to solve some material science problems and chemistry problems, and they found that it wasn't all smooth sailing. The reasoning that came out was sometimes, and the comprehension was sometimes not so good. And they suggested a certain standardization method. You're always going to get a different output, maybe for the same prompt. You might always not get the same output. They also said we need to have, this is some time ago, more tools that connect with the LLM in order to get more accuracy with a sort of a user interface like this. I thought this was a standardization opportunity, and as an educator as well, I also wonder if so I wanted to put forward the idea that we actually use for agents which do reasoning, come to that in a second, and use something like Bloom's taxonomy, which is a measure of how students learn. And so in principle, you can think about applying something to how an LLM might explain something back to us. So I think there's room here for more than just accuracy, reasonableness, and completeness in measuring the output of a text output or explanation of a concept using something like ChatGPT. So automation, I'll fly through this as well, because this is just one piece that takes us from LLMs into a subworld that's automation by itself, using robots. Alan Asprey-Guzik has got the Organa that's going on here, and there's a lot of other work that does work on automation. But the problems with automation as defined here is that there are, automation is often limited to predefined instructions. We don't get feedback. We don't have this feedback loop within the automative cycle. And I think the solution here is the agents. So the last few minutes, I'll talk about agents. This was really Mike Caldas Ramos's piece of the review. So what we do is we describe agents, though, and let's define this agent as working. There's an external environment, and then what the agent does. And so our definition was an agent continuously receives observations from that external environment. It executes actions to complete a provided task. It has these internal agent modules, and it has these external tools. So the tools aren't part of the agent. So there's opportunities for people to work on tools, and it might actually be any of these LLMs predicting syntheses that might be a different tool that gets used by the agent, the central nervous system, if you will. But the agent makes you can train it to do decision making, and then there are these external pieces. So the main actions: memory, planning and reasoning, profiling, perception, and tools. So I'll quickly sort of go through those. Memory, the main thing here is, there's three types of memory. There's so the embedded knowledge. You can pre-train these agents. So that's the embedded knowledge. Then there's in context, the context window that you can there's task specific, and then you've got long-term memory, which is maybe store the information you've gathered externally. But a lot of people are working on the context window compression here, vectorizing that to compress the in context memory, if you will. So that's internal. We've got planning and reasoning. So these are the main ideas. So what the LLM will plan, what are the action sequences it needs to do to achieve the goals, and it's going to reason, so draw conclusions, based on whether it's got there or not. So these concepts as chain of thought. Again, the review goes into it in a little bit more detail. Generating even new context tokens here. You always get this feedback and verification, which makes this different from just pure automation. So we've got these reflections and these questions that an agent, a different LLM, can generate questions to test and verify whether the agent has actually completed its task. And then we've also got different ways that we can improve this, even with a human in the loop. Another thing, you've probably all recognized that with profiling we can actually change the view of the change the LLM role. We tell it it's a professor, or tell it and the professor talks too much, right? And et cetera. So we can change it by inputting psychological characteristics. So that's the internal piece. The external piece, this is the key, right? We've got to have some perception as to what's going on outside. We may want to get multimodal information. So there's that multimodal piece that becomes really important for agents. So developing videos into or images into some comprehensible format for the LLM. That's on the outside here. And so what else? And then there's also the tools itself. So how does the agent decide what tools to use? It goes to the action space, or it might just use every tool that it's got available to it. So these LLMs can be pre-trained. And I realize what I've done in here right now is I've kind of put together a summary of the summary that was in the paper. But again, Mike was working on this particular piece, and I've kind of worked on most of the front end. Good grief! This is a slide that basically says so there's some early history here. So Hockey and Andrew White, and this is Mike Caldas Ramos did some work. This is all very recent, right? And Kevin Jablonka's group, they had a hackathon, and there were 14 different ideas for building agents in this as part of this hackathon. And there's this 14 examples paper that really started to show the world what could be done. And then the last couple of slides, again, is a little bit of a plug for the one that I'm more familiar with, but there's ChemCrow and Chemist X, and then Gabe Gomez's group came up with Co-Scientist as well. So more or less the same thing, in that we're automating lab tasks. So I'll jump to the ChemCrow video slide in here. And what ChemCrow did, not super highly sophisticated chemistry, right? But chemistry that could be done. You have an agent that searches for a synthesis from the web, comes up with a synthesis plan, develops code to write to the robot to get the robot to synthesize the material. You measure the properties of the material using some connection to I forget what was used in the paper, mass spec or UV vis, for example, here to actually measure that you've got the right the molecule. It was a fluorophore or chromophore in here. So you put all these things together and that becomes your agent. So we can now work on individual tools, different groups to work on individual tools, and we can take that domain expertise and bring it together through the agent. Future directions and applications. I'm going to kind of jump to a summary of challenges and opportunities, and I'll sort of highlight this. To me is now the part that's really interesting, because this is about where we go. So sure, with LLMs and chemistry, we can increase accuracy and efficiency. I showed you so many slides where we're sort of incrementally improving the accuracy and the efficiency. The agents is really exciting now because we can bring a lot of these ideas together. Democratization is another important point here. Different domain knowledge can be brought into these agents. And what else? Another thing I haven't talked much about, there's so much to talk about, but data quality and availability. We use these benchmarks that have very narrow sets of drug protein target pairs. And so if we're always training our models to outperform somebody else's model based on that single combination of target and drug, then we may not be so generalizable. We might not be able to apply to a broader set of problems. And I think this is a big problem. And I think there's lots of opportunities to actually get more data. The models improve with a greater scale of input data. So this is kind of these two bullets down here. Multimodal work is a great opportunity to pull information from scientific papers. Andrew's paper QA is perhaps one idea. There's some good work. Jackie Cole, I think, and a lot of good work on paper scraping and coming out of the different research groups. Model interpretability. Haven't said much about this, but using, trying to explain or using, trying to pull some mechanistic understanding out of something that's essentially data driven. The accuracy is data driven. There's always the issue of potential misuse, right? And so these things come up as well. And then how do we improve human AI collaboration? I didn't think I'd take this long, actually, but I kind of got into it. LLMs are kind of transforming our research, right? I still think there's a gap between AI and chemical sophistication. So on one axis, we've got AI sophistication, and on the other axis, chemical sophistication. We're not necessarily applying that AI, or we're not able to apply the AI to perhaps the really high impact problems, carbon sequestration, that we might care about in the world. So I think there's an opportunity here as well. And the last plug would be for this this repo, this repository of LLM studies that Mike's going to update that with using an agent. And I got to thank, this is some other pictures that are interesting. We've got to thank a few other people who helped review our paper. And then thanks for Mike and Andrew for the working together on this review. So thanks for indulging me on a Friday afternoon. And I'll stop there and see if there's any questions.
Yeah, this is fantastic, Chris. Also, it's exciting to have you close because we listened from many of the people that have built various elements of this through the summer school. So it's great that you've been able to round it out. Um, do you do you think you could just walk through the GitHub of just how it's organized,
Um,
or
I'm gonna say, I mean, I could, I'd be flying blind pretty much. So
but
that's
maybe just if you could just go there, I think just for the video sake, right? If we just have a walkthrough, I think maybe we'll all walk through it together, right? So
that sounds good. Let's see if I can so you can see my, let me stop sharing and see if I can get a window up here. All right, let me start sharing again. This is what we get.
Yep.
So this is basically where he's got the publications. So you can kind of click on any of the publications, and he's got them listed by date. And then I think his agent tells him, it puts things in a bin for him to review. And I think we were laughing because I think this is a big job. There's already, I mean, this is totally eye-opening. All this work that we've kind of gone through. But he's got a big job to keep adding things to
agent to summarize the agents, right? So
but there you go. I think I'm not sure if he's
so I think
he's
that's the
there's a
agents.
repository
Yeah, the
for it as
GitHub
well.
repos are there. Yeah. And
So
then
I'm
I guess the
glad
name talks about what kind of methods and ideas are, I guess, there, right?
Yes. So what has he got? So this is the so he's got SciLLM and Sci agents.
Great. So these are agents in the scientific context that people have built.
I'm happy to click on something if you.
Yeah. No, this is perfect. Yeah, I think this is good enough. So, yeah, I think those in the audience, yeah, feel free to I put the GitHub link on the chat, and then we'll put it on the summer school website, and then I think there's a lot of exciting resources here to go over. Okay, we're at the very end, so maybe I'll just ask one question and then close this out. So thank you for sort of a very detailed overview, and I think it also shows that at the beginning of this meeting, right? We sort of talked about what are the areas where we expect sort of most likely big outcomes from these language models, and one of the sort of two main areas that emerged was chemistry or material science and biology, especially around genomics and things of that kind, right? Where there's a natural text representation, and you sort of have summarized that very well. Now, I think one other topic that we've sort of been debating over the entire summer school is the notion of novelty and sort of what would what would surprise maybe what would surprise Chris, right? Like if an LLM sort of came up with a hypothesis of here's or an agent sort of found a particular new molecule for a particular chemistry or materials application or biology. I think that is sort of still, I guess, that killer application is sort of remains to be seen, right? Whether it can actually get there. And so I'm curious if you were to sort of wager, resources in one particular thrust and say, okay, here's where I would sort of bet my resources to sort of go after this problem. Maybe one or two topic areas so that that can inspire people in the audience to sort of think through that.
Yeah, I think well, without answering the question directly, first I will say I think we need to have humans in the loop, because there are sometimes things that are going to be surprising, and we may not even be able to recognize. So this fantastic new drug that somebody generates, we take the LLM, we start using it. I can't say what the drug companies are doing, but I'm not sure my colleagues are using some of these models. But this fantastic new drug, we have to have, I think, the humans around. We've got to be working with this as a tool, just like we use calculators as. But in answer to your question, I also have to think back about what the metal organic frameworks, the sort of burst of work that's come out on metal organic frameworks, and who knew? I didn't know that would come out, but that is, to me, it's about carbon sequestration. And so looking backwards, I don't have the right crystal ball, but I can look backwards and say, hey, that was really good. I don't know what next will come. I think there's a lot of people working on drugs for different protein targets. I wouldn't be surprised if we could come up with some data sets where we have different binding receptors, and maybe even in industry they've already got their own benchmarks that they're working with, because that's what they're aiming towards. And it's, the benchmarks are private in those particular worlds. So I still think the cynical part of me also says let's go to where the money is as well, right? So I think the pharmaceutical industry is going to probably be tackling this as well. So I wouldn't be surprised if something came out. I'm not even too sure the role that with COVID that machine learning had there, but I suspect that was quite substantial. So my crystal ball says probably still look at drugs and pharmaceuticals. But I think we could probably end up having this conversation around the table for a long time, different people coming up with their own high priority target area.
Yeah, I think I think that would be that would be a good good place to try, right? I think obviously lots of diseases, so it's exciting chemical space, and I think MOFs are also very interesting, and I think I guess Cusp AI, one of Max Welling's efforts is trying to go after MOFs. So I think we'll I guess maybe watch back in SciFM 28 whether they have indeed actually gone ahead and found a new MOF to sort of do carbon capture. So
I think just very last 10 seconds. I also think maybe we can do the chemists. I hope can do a better job of connecting with the AI people, and the AI people can do a better job of connecting with the chemists. Because I think it's that overlap that we need to, chemists, can we embrace AI and AI? We're not going to be able to find those key applications unless we perhaps start to promote what we can do in a way that's intelligible to the chemists. And that's my thought. I'll stop there.
Yeah, fantastic. Okay, thank you so much, Chris, and thanks to everyone for tuning in throughout the week. And then I look forward to continuing. I think we have 4 exciting thrusts in the hackathon over the next 2 weeks. So we'll see how far we can get. All right. Thanks, everyone. And then have
Thanks
a
for
great
having me.
weekend.
Yep.
Bye.